Picture the most breathtaking image of a galaxy you have ever seen. Perhaps it's the Whirlpool Galaxy, with its graceful spiral arms swirling in shades of blue and pink, a stellar nursery glowing with newborn stars. Or the vibrant core of Andromeda, a brilliant yellow-white beacon surrounded by a haze of countless suns. For centuries, we've looked up at the cosmos and seen a tapestry of color, a universe painted with an artist's palette. But what if you looked through a powerful telescope and saw something that defied this beautiful logic? What if you found a galaxy that emitted only one single, unwavering color? This is not a thought experiment. It is not science fiction. This is a genuine and deeply perplexing astronomical mystery that exists in our skies today, a cosmic anomaly that challenges the very foundations of what we know about how galaxies live and die. It forces us to ask a question so fundamental it seems almost childish. Why would the universe create something so strange, so monotonous, and so utterly unlike anything else we have ever found? This is the story of a cosmic outlier, a galaxy that shines with a singular hue, presenting a puzzle that has left the world's brightest astronomers scratching their heads. We are going on a journey to the edges of our understanding, to a place where the normal rules of physics seem to have been rewritten. This single-color galaxy isn't just a curiosity, it is a key. It has the potential to unlock secrets about the life cycles of galaxies, the behavior of matter under extreme conditions, and perhaps even reveal new, fundamental laws of nature that have been hiding in plain sight. The existence of such a place pushes against the boundaries of our knowledge, forcing us to reconsider what is possible in the vast expanse of space. It's a reminder that the universe is far stranger, far more inventive, and far more mysterious than we often give it credit for. So prepare to dive into one of the most intriguing enigmas of modern astronomy. We will explore the leading theories scientists have proposed, from the ghostly glow of ancient stellar fossils to the possibility of exotic, unknown forms of matter. We will investigate how such a bizarre object could even form, and what its lonely, monochromatic light tells us about the past and future of the cosmos. This is a detective story written on a galactic scale, and you are about to become part of the investigation. The mystery of the galaxy that emits only one color is waiting, and the answers we find might just change our view of the universe forever. The galaxy that has captivated and confounded astronomers goes by the unassuming name of PGC 04511112. Located an astounding 750 million light-years away in the constellation of Lynx, this distant island of stars should, by all accounts, look like a faint, fuzzy smudge of blended starlight. But it does not. When we point our most sophisticated instruments toward it, the data we receive is starkly simple. Instead of the expected symphony of wavelengths, the brilliant blue of hot, young stars, the steady white of middle-aged suns like our own, and the deep red of aging giants, we detect only one powerful, dominant note. This galaxy emits an intense and pervasive red light, specifically at the wavelength known to astronomers as hydrogen alpha. To understand just how bizarre this is, we need to think about what makes up a typical galaxy. A normal spiral or elliptical galaxy is a diverse cosmic community. It contains stars of all ages, sizes, and temperatures. A hot, massive star, for instance, burns ferociously and gives off most of its energy in the blue and ultraviolet parts of the spectrum. A cooler, older star radiates a calmer, redder light. When you combine the light from billions of different stars along with the glowing gas clouds they illuminate, you get a broad spectrum of colors, a blended whitish light, similar to the light from our own sun. This is why most galaxies appear to our telescopes as a complex mixture of wavelengths. PGC 04511112 shatters this expectation. The dominant red glow it emits comes from a very specific atomic transition within hydrogen gas. Essentially, Vast clouds of hydrogen throughout the galaxy are being energized, causing their electrons to jump to a higher energy level and then fall back down, releasing a precise photon of red light each time. This is not unusual in itself. We see this hydrogen alpha emission in nebulae all over our own galaxy. The profound mystery is that in PGC 0451112, this single, specific red emission is almost the only light we see. It's as if the entire galaxy has been reduced to a colossal, singular emission nebula, with almost no sign of the diverse stellar population that should be there to power it. The symphony has been replaced by a solitary, unwavering hum, and astronomers are left to figure out what kind of cosmic instrument could possibly produce such a pure and lonely tone. The first hint that something was profoundly unusual about this patch of sky came not from a dramatic image, but from a cold, digital readout. It was within the colossal astronomical database of the Sloan Digital Sky Survey, a project that has methodically mapped over a third of the night sky, cataloging hundreds of millions of celestial objects. For the astronomers sifting through this ocean of data, PGC 0451112 initially appeared as just one more entry among countless others. But its spectrum, the unique fingerprint of light that reveals the chemical composition and physical state of an object, was unlike anything they had ever encountered. Instead of the familiar peaks and troughs corresponding to a mix of elements from a varied stellar population, the graph showed an overwhelming, towering spike at one specific wavelength, the red hydrogen alpha line. The rest of the spectrum was eerily flat, almost silent. It was as if someone had taken the complex musical score of a galaxy and erased all the notes except for one, played at a deafening volume. The initial reaction among the small team who first noticed this anomaly was not excitement but profound skepticism. In astronomy, the simplest explanation is almost always that something is wrong with your equipment or your data. They immediately began a rigorous process of elimination. Could this be a glitch in the spectrometer? They checked the data from other objects observed right before and after this galaxy. Their spectra were perfectly normal. Could it be an error in the data processing pipeline, a bug in the software that analyzes the raw light? They reran the numbers multiple times, each calculation confirming the bizarre result. Perhaps they thought it was a much closer object, a simple cloud of hydrogen gas within our own galaxy that had been misidentified as a distant galaxy. But measurements of its redshift, the stretching of light waves due to the expansion of the universe, placed it firmly at a distance of 750 million light-years. There was no escaping the conclusion. The signal was real, it was distant, and it was, by every conventional standard, impossible. This moment of verification is a pivotal point in science, the tense transition from disbelief to the thrilling, and sometimes unsettling, acceptance of a genuine mystery. The astronomers knew they were no longer looking at an error, but at a window into a cosmic process they did not understand. The galaxy's starkly monochromatic light presented a paradox that challenged textbook definitions. A galaxy, by its very nature, is a gravitationally bound collection of stars, gas, and dust. PGC 0451112 had the gas, evident from the powerful hydrogen emission, but where were the stars that should be illuminating it? The sheer intensity of the red glow implied a tremendous source of energy, yet the light from the stars themselves was conspicuously absent. This set the stage for a deep and compelling cosmic whodunit, forcing scientists to ask what kind of power source could possibly light up an entire galaxy in one single, pure color while leaving almost no other trace of its existence. Faced with such a baffling signal, the scientific process demands that you start with the simplest, most mundane explanation. The leading hypothesis, the one every astronomer would bet on initially, is that we aren't seeing the galaxy's true nature at all. Instead, we might be witnessing a cosmic illusion, a trick of light and shadow on a galactic scale. The culprit, immense, dense clouds of cosmic dust. Think of it like seeing car headlights on a foggy night. The thick fog scatters the bright white light, allowing only the longer, redder wavelengths to pass through, making the lights appear dim and red. Could a similar phenomenon be happening with PGC 04511112? Perhaps this galaxy is actually quite normal, bustling with a full population of stars of every color, but it is shrouded in a mammoth veil of dust so thick that it blocks almost all the starlight, only permitting that one specific shade of red hydrogen light to escape. This is a perfectly reasonable theory because interstellar dust is common. Giant molecular clouds, the birthplaces of stars, are filled with tiny grains of carbon and silicon, essentially soot and sand, that are excellent at absorbing and scattering blue light. To test this dust obscuration theory, astronomers turned to a powerful tool, infrared astronomy. Infrared light has longer wavelengths than visible red light, allowing it to slip past the tiny dust grains relatively unscathed. If a thriving stellar population was hidden behind the dust, infrared telescopes would act as cosmic night vision goggles, revealing the warm glow of all those obscured stars. Observatories like the Spitzer Space Telescope were pointed at the galaxy, scanning for the telltale heat signature of a hidden universe. The results, however, were not what the dust theory predicted. The infrared observations revealed no great reservoir of hidden stars. There was no significant excess of heat, no indication of a vast, obscured stellar metropolis. The galaxy was just as quiet in the infrared as it was in the other colors of light. This was a critical blow to the simplest explanation. It meant the monochromatic nature of PGC 04511112 was not a trick of perspective, it was an intrinsic property. The galaxy wasn't hiding its diversity. The evidence increasingly suggested that the diversity simply wasn't there to begin with. This ruling out of the obvious deepened the mystery exponentially, transforming it from a potential case of cosmic camouflage into a genuine question about the galaxy's very composition and history. The foggy night analogy had broken down. It wasn't that the headlights were hidden, but that the car itself might be nothing more than a single, strangely persistent red bulb. With a dust theory failing to explain the eerie silence in other wavelengths, astronomers had to consider more dramatic possibilities. What if the galaxy isn't dormant or obscured, but is instead experiencing a celestial cataclysm of unimaginable scale? This line of thinking leads to one of the most violent and spectacular events in the universe, a starburst. A starburst galaxy is one undergoing an explosive frenzy of star formation, a period where gravitational collapse triggers the birth of stars at a rate hundreds or even thousands of times faster than in a normal galaxy like our Milky Way. These events are often sparked by galactic collisions or close encounters, where immense clouds of gas are violently shaken and compressed, igniting a firestorm of new stars. In such a ferocious environment, the stellar population becomes heavily skewed. An overwhelming number of the stars born are incredibly massive blue-white giants. These are the rock stars of the cosmos. They live fast, burn hot, and die young. A star like our Sun can shine steadily for billions of years, but a truly massive star might only last a few million. While they exist, they are powerhouses, emitting most of their energy in the ultraviolet part of the spectrum. This intense UV radiation then floods the surrounding clouds of hydrogen gas, violently ionizing the atoms and causing the entire nebula to fluoresce with that characteristic brilliant red hydrogen alpha glow. So, if PGC 04511112 were an extreme starburst, its intense red light could simply be the signature of a galaxy-sized neon sign, powered by the searing ultraviolet light from countless newborn stellar behemoths. This theory holds a lot of initial appeal. It accounts for the sheer power of the hydrogen alpha emission and provides a logical reason why the galaxy's light might be dominated by a single process. However, when we look for the other essential clues that a true starburst leaves behind, the evidence for this galaxy becomes frustratingly weak. The first major discrepancy is the lack of other emission lines. The violent environment of a starburst doesn't just excite hydrogen, it also energizes other elements like oxygen and nitrogen. The spectra of known starburst galaxies are a complex fireworks display of multiple emission lines at specific wavelengths. PGC 0451112 spectrum, by contrast, is starkly simple, almost pure hydrogen. It's as if you had a chemistry set where only one element was reacting. Furthermore, that intense ultraviolet light from massive stars doesn't just vanish after ionizing the gas. A significant portion of it should be absorbed by surrounding dust clouds, which would then re-radiate the energy as a powerful glow in the far infrared. This infrared warmth is a hallmark of starburst galaxies. They are among the brightest infrared objects in the sky. Yet, as we discussed, infrared observations of our mysterious galaxy show no such excess. The energy input required to light up all that hydrogen is enormous, and if it were coming from young stars, we would absolutely expect to see the thermal byproduct. The fact that we don't suggest the power source is something far more exotic, something that energizes the gas without also producing the other predictable signatures of a stellar baby boom. The starburst hypothesis, while thrilling, ultimately creates as many questions as it attempts to answer, leaving the core mystery of the galaxy's solitary red glow more profound than ever. When the most conventional explanations fall short, science must turn to the truly extraordinary. This brings us to a far more radical yet compelling hypothesis for our monochromatic galaxy. What if the light we see isn't coming from stars at all? What if it is the brilliant, focused glare from the most powerful engine in the known universe, a supermassive black hole in its most active and violent phase, known as a quasar? At the heart of many large galaxies, including our own Milky Way, sits a supermassive black hole, a gravitational pit so deep that not even light can escape. But it's not the black hole itself that shines, it's the frenzied whirlpool of matter surrounding it. As vast amounts of gas, dust, and even entire stars are pulled inward by the black hole's immense gravity, they don't fall straight in. Instead, they form a rapidly spinning, superheated structure called an accretion disk. The friction and gravitational forces within this disk are so titanic that they heat the material to millions of degrees, causing it to glow with an intense, blazing light across the entire electromagnetic spectrum, from X-rays to radio waves. This is a quasar, an object so luminous it can outshine every single star in its host galaxy combined. The connection to our mystery seems promising. A quasar's incredible energy output could easily be the power source needed to excite the vast hydrogen clouds throughout PGC 0451112, creating the intense red glow we observe. But there's a critical detail that makes this theory so specific to our case. A typical quasar is a cosmic broad-spectrum spotlight. Its light is a messy, complicated mix of every wavelength, generated by a chaotic maelstrom of physical processes in the accretion disk and its associated jets. The spectrum of a normal quasar is a forest of intense, broad emission lines from many different elements, superimposed on a bright, continuous background. Our galaxy's spectrum is nothing like that. It is a clean, almost minimalist spike of hydrogen alpha light. So the question becomes, could a quasar's light be filtered or manipulated in some way to produce such a pure, singular signal? Scientists theorize that under very specific and rare conditions, this might be possible. Imagine the quasar is not positioned face onto us, but is instead surrounded by a thick, donut-shaped ring of gas and dust called a torus. If we are viewing this system from the side, looking through the outer layers of this torus, the structure could act as a colossal cosmic filter. The torus would block the direct, messy light from the blazing accretion disk itself, The X-rays, the ultraviolet, the broad emission lines, but it might be porous enough to allow the quasar's immense energy to leak out and illuminate a much larger reservoir of hydrogen gas that surrounds the entire galactic center. In this scenario, the hydrogen throughout the galaxy is being lit up by the quasar's power, but we are only seeing the light emitted by that specific gas cloud, not the central engine. It would be like seeing a city illuminated at night from a great distance. You see the glow of the streetlights, but the power plant generating the electricity is hidden from view. The properties of that glowing gas, not the light source itself, would determine the color we see. To confirm or refute this quasar hypothesis, astronomers need to go hunting for the hidden monster. The most telling evidence would be the detection of specific signatures that are the unmistakable fingerprints of an active galactic nucleus, even an obscured one. The first clue would be in the radio waves. Many quasars propel gigantic jets of charged particles at nearly the speed of light, and these jets emit strongly in the radio part of the spectrum. A deep, high-resolution radio observation could reveal whether such jets are present, pointing directly to an active black hole. The second line of evidence would come from the infrared. While the torus blocks visible light, it absorbs the quasar's furious energy and heats up, glowing brightly in the infrared. A targeted search for this specific infrared heat signature would be a major step toward confirmation. Finally, and most definitively, astronomers would look for subtle, high-energy signatures. Even through the obscuring torus, some high-energy X-rays might penetrate. Space telescopes designed to observe the X-ray universe could be pointed at the galaxy, searching for the telltale flicker of a hidden, feeding black hole. Finding any of these signs would transform our understanding of PGC 0451112 from a bizarre outlier into a rare and valuable cosmic laboratory, offering a unique perspective on how the most violent objects in the universe can shape their surroundings. But what if the answer lies not in the present-day violence of a black hole, but in the universe's deepest past? To explore this possibility, we must journey back in time, to an era before planets, before galaxies as we know them, even before most of the elements that make up our world existed. This leads us to the most profound and poetic hypothesis for our monochromatic galaxy. The idea that we are not looking at a modern anomaly but a living fossil. A cosmic relic that has somehow survived from the dawn of creation, composed of the very first stars to ever shine. These first stars are known to astronomers as population 3 stars. Our own Sun is a population 1 star, rich in heavy elements like carbon, oxygen, and iron elements that were forged in the hearts of earlier generations of stars and scattered across space by supernova explosions. But in the very beginning, the universe contained only the 2 simplest elements, hydrogen and helium, created in the Big Bang. Population 3 stars would have formed from this pristine, primordial gas, a material of perfect purity. Without any heavier elements to help the gas clouds cool and fragment efficiently, theory suggests these first stars would have been monstrously large, hundreds of times more massive than our Sun. Such behemoths would have lived spectacularly short and violent lives, burning at temperatures so extreme they would have emitted a tremendous amount of their energy as intense ultraviolet radiation. This is where the connection to our red galaxy becomes tantalizing. That fierce ultraviolet light from a galaxy full of population 3 stars would have acted exactly like the energy from a quasar, but on a galactic scale. It would have flooded the surrounding hydrogen gas, causing it to fluoresce with that same characteristic red hydrogen alpha glow. The key difference, however, is in the signature. A galaxy powered by these first stars would have an astonishingly pure spectrum. Since the stars themselves are made only of hydrogen and helium, and the gas around them is equally pristine, there would be no significant emission lines from oxygen, nitrogen, or sulfur. The light we would see would be dominated almost entirely by hydrogen, a perfect match for the stark, simple spectrum of PGC 0451112. It would be a galaxy emitting the universe's first and most fundamental color. Finding such a relic would be the astronomical equivalent of discovering a living dinosaur. It would provide a direct observational window into the conditions of the early universe, allowing us to test our theories about how the first stars and galaxies formed. We could study their life cycles, their incredible masses, and their role in ending the cosmic dark ages by flooding the universe with its first light. The implications would be revolutionary, yet this beautiful theory faces a significant challenge: time. Population 3 stars were, by their very nature, unstable and short-lived. They were predicted to have burned out and exploded in spectacular supernova within just a few million years of their birth, polluting the cosmos with the first heavy elements and paving the way for the more stable stars that followed. The universe is nearly 14 billion years old. How could a galaxy composed of such transient objects have persisted until today, 750 million years ago from our perspective? One possibility is that we are witnessing a late bloomer. Perhaps this galaxy formed in a region of space that was unusually barren, a cosmic desert where the gas remained pristine for billions of years longer than anywhere else. Isolated from the polluting winds of earlier supernova, this pocket of primordial gas could have finally collapsed to form its first stars long after the rest of the universe had moved on. Alternatively, maybe the galaxy is not entirely composed of true population 3 stars, but of a second generation of stars that formed from gas that was only lightly enriched. These stars would still be incredibly pure and hot, behaving in a very similar way, and could potentially form much later in cosmic history. The intense, monochromatic red light would then be the signature of this last bastion of stellar purity, a final echo of the universe's fiery birth in a cosmos that has otherwise become complex and contaminated. This idea transforms the galaxy from a mere curiosity into a potential time capsule, offering us a unique glimpse into a chapter of cosmic history that was thought to be lost forever. Yet, with even these exotic explanations, we might still be thinking too small. What if the power source for this galaxy's strange light is not anything made of ordinary matter at all, but stems from the invisible, mysterious substance that makes up the vast majority of the universe's mass, dark matter? This idea pushes the mystery into the realm of theoretical physics, proposing that PGC 0451112 could be a unique laboratory for observing the behavior of this cosmic ghost. We know dark matter exists because of its gravitational pull. It guides the rotation of galaxies and bends the fabric of space itself, but we have no idea what it actually is. For decades, physicists have proposed numerous candidate particles, and some of these theoretical entities could, under the right conditions, produce light. One leading candidate is a class of particles known as WIMP, or weakly interacting massive particles. The theory suggests that when 2 WIMP collide, they could annihilate each other in a flash of energy, transforming their mass into other particles, which could then decay and ultimately produce standard photons of light. This process would be incredibly subtle and spread out across a vast volume of space, which is why we haven't detected it directly. But what if this galaxy is different? Imagine a scenario where it is unusually rich in dark matter, perhaps because it is the dense, leftover core of a much larger galaxy that was stripped away. Within this concentrated halo, the collision and annihilation rate of dark matter particles could be significantly higher. Instead of a faint whisper, it could generate a steady, pervasive hum of energy. This energy would then be deposited into the galaxy's hydrogen gas, causing it to glow with that specific red light we observe. The process would be remarkably uniform and monochromatic because it would be governed by the fixed properties of the dark matter particle itself, unlike the messy and varied energy output of stars or quasars. An alternative and equally mind-bending possibility is that the dark matter particles are not annihilating but slowly decaying. Some theories suggest that dark matter may not be perfectly stable over trillions of years. A small fraction of these particles could be spontaneously transforming into particles of light and other known matter. If this is happening, then every cubic light-year of space filled with dark matter would be faintly glowing. In most galaxies, this feeble light would be completely washed out by the brilliant glare of billions of stars. But in a galaxy that lacks a stellar population, a galaxy that is, by chance, mostly dark matter and hydrogen gas, this soft, universal glow could become the dominant source of light. It would be a gentle, pervasive illumination with a very specific color, determined solely by the mass of the decaying dark matter particle. In this scenario, the red light of PGC 04511112 would not be a beacon of violent activity, but the serene, intrinsic light of the universe's hidden mass slowly revealing itself. The implications of either dark matter explanation would be nothing short of revolutionary. Confirming that the galaxy's light comes from dark matter interactions would be the first ever direct detection of what this mysterious substance is made of. It would catapult our understanding of particle physics forward by centuries, allowing us to move from inferring dark matter's existence through gravity to actually studying its properties and behavior. This one strange red galaxy could provide the experimental evidence needed to validate entire branches of theoretical physics, finally cracking one of the greatest mysteries in modern science. It would transform astronomy and cosmology, giving us a new tool to map the dark matter distribution throughout the cosmos and understand its fundamental role in shaping the universe we see today. The mystery of this single-color galaxy would then become far more than a cosmic curiosity. It would be a keyhole through which we could peer into the hidden 95% of the universe that has, until now, remained completely in the dark. Yet another possibility exists, one that turns the entire mystery on its head. What if the strangeness of PGC 04511112 is not a property of the galaxy itself, but a grand illusion created by the fabric of the universe? This theory suggests we might be witnessing a cosmic mirage, a trick of light orchestrated by one of Einstein's most fascinating predictions, gravitational lensing. According to Einstein's theory of general relativity, massive objects warp the very fabric of space and time around them. Think of space as a taut, flexible rubber sheet. Placing a heavy bowling ball in the center creates a deep depression. Now, if you roll a marble across that sheet, its path will curve as it follows the contour created by the bowling ball. Light behaves in exactly the same way. Even though it has no mass, a beam of light will follow the curved path created by a massive object's gravitational field. An entire galaxy cluster containing the combined mass of thousands of galaxies, trillions of stars, and immense quantities of dark matter creates a gravitational pit so profound that it can act as a colossal, natural lens in space. It bends and distorts the light from objects that lie far behind it, sometimes magnifying them, sometimes creating multiple images, and sometimes twisting them into strange, elongated arcs of light known as Einstein rings. So how could this explain our single-color galaxy? Imagine a completely normal background galaxy, rich with stars of all colors, situated directly behind a massive foreground galaxy cluster. As its light travels toward us over hundreds of millions of light years, it must pass through the intense gravitational field of this cluster. This lens does not act like a simple glass lens. It is a complex filter that can manipulate light in subtle and powerful ways. One possibility is that the lens is not just bending the light, but also acting as a chromatic filter. Different wavelengths of light can be bent by slightly different amounts, a phenomenon known as chromatic aberration. Under extremely specific and rare alignments, it's theoretically possible that the gravitational lens could be configured to focus and magnify only a very narrow band of wavelengths specifically. the red hydrogen alpha light, while scattering or diffusing all the other colors from the background galaxy. From our vantage point on Earth, we would see a brilliantly magnified monochromatic image of the galaxy, while the rest of its light is effectively lost, spread out into an undetectable haze. The galaxy itself would be perfectly ordinary, but the cosmic lens through which we are viewing it would create the illusion of a single-color anomaly. Astronomers are well versed in hunting for the signs of gravitational lensing, as it is a common tool used to study the most distant objects in the universe. To test this hypothesis for PGC 0451112, they would embark on a meticulous forensic investigation. The first and most telling clue would be the galaxy's shape. A strongly lensed object is rarely seen as a perfect, undistorted smudge. The gravitational warping typically stretches it into a distinct arc or reveals multiple mirrored images of the same object arranged symmetrically around the lensing cluster. The first step, then, is to obtain the highest resolution image possible of that patch of sky, likely using the Hubble Space Telescope or the James Webb Space Telescope. They would search for any telltale elongation, arc-like structure, or faint duplicate images that would betray the presence of a foreground lens. If the galaxy appears perfectly symmetrical and isolated, with no signs of distortion, the lensing hypothesis becomes much less likely. Next, they would work to identify the suspected lens itself. They would meticulously map the region in front of the mysterious galaxy, searching for a massive galaxy cluster that lies along the same line of sight. Using redshift measurements, they could confirm whether any such cluster is indeed closer to us than PGC 0451112. Finding a suitable lens candidate is crucial. However, even if a cluster is present, its gravitational influence must be precisely aligned to produce the strange filtering effect. Astronomers would create sophisticated computer models of the cluster's mass distribution, based on the visible galaxies and the inferred dark matter, and then simulate how it would bend the light from a background galaxy. They would run countless simulations to see if any configuration could possibly result in the pure, single-emission spectrum we observe. If the models consistently show that the lens would produce multiple images or a broad spectrum of light, then the mirage theory, while elegant, may not hold up to scrutiny. This painstaking process of observation and simulation is essential for separating a true cosmic anomaly from a breathtaking, but ultimately explainable trick of the light. The simplicity of the light from this galaxy points directly to an even more fundamental simplicity in its very ingredients. The tool that allows us to peer into a galaxy's chemical soul is spectroscopy, the same technique that revealed its strange light in the first place. Every element in the periodic table, when heated or energized, emits light at a unique set of wavelengths like a fingerprint. By spreading a galaxy's light into a rainbow and looking for these specific dark absorption lines or bright emission lines, astronomers can conduct a cosmic chemical analysis from millions of light years away. They can determine not just what elements are present, but also in what proportions. And this is where our galaxy presents another profound clue. The spectrum of PGC 0451112 is not just dominated by hydrogen. It is also strikingly devoid of the signatures of heavier elements, what astronomers call metals. In the language of astronomy, any element heavier than helium is considered a metal. This includes carbon, oxygen, nitrogen, iron, all the fundamental building blocks of planets, life, and indeed, the complex chemistry that governs how stars form and behave. A galaxy's metallicity is a measure of its chemical maturity. Our own Sun, for instance, is a metal-rich star, containing about 1.5% of its mass in these heavier elements, a testament to the fact that it formed from gas that had been enriched by countless generations of earlier stars that lived and died before it. A normal, evolved galaxy like the Milky Way has a rich and complex chemistry. But what if a galaxy has somehow avoided this cosmic pollution? If a galaxy is metal poor, it means it is composed almost entirely of the pristine, primordial hydrogen and helium that have existed since the Big Bang. This lack of heavier elements has a dramatic effect on the types of stars that can form within it. Heavier elements are crucial for cooling giant gas clouds. As a cloud collapses under gravity to form stars, these metals allow the cloud to fragment into smaller, more numerous clumps. In a metal-rich environment, you get a wide variety of stars from small red dwarfs to massive blue giants. But in a metal-poor environment, the physics changes entirely. Without those heavier elements to aid cooling, the gas cloud cannot fragment as efficiently. This leads to the formation of stars that are, on average, much more massive. And massive stars are incredibly hot, burning at ferocious temperatures that cause them to emit most of their energy in the ultraviolet part of the spectrum. This creates a direct link between chemical composition and color. A galaxy teeming with massive, hot, metal-poor stars would flood its surroundings with intense ultraviolet radiation. This UV light would then powerfully excite the surrounding hydrogen gas, causing it to fluoresce with that brilliant, characteristic red hydrogen alpha glow that we see so strongly in PGC 0451112. At the same time, the galaxy would lack the cooler, older, redder stars that typically provide balance in a normal galaxy's spectrum because those massive stars burn out so quickly. They simply don't live long enough to evolve into a stable, diverse population. The result could be a galaxy whose light is overwhelmingly dominated by the single process of hydrogen emission, a direct consequence of its chemically primitive state. It would be a galaxy stuck in its youth, forever shining with the brilliant, monochromatic light of its first and most massive generation of stars. To truly grasp the nature of this cosmic enigma, we need to shift our focus from the grand power sources to the very substance that's actually glowing, the galaxy's interstellar medium. This is the raw material that fills the space between stars, a diffuse mixture of gas, mostly hydrogen, and microscopic dust grains. In a typical galaxy, this medium is a complex and dynamic environment, with pockets of extreme cold and blistering heat, regions of near-perfect vacuum and dense molecular clouds. It's this diversity that normally creates a rich tapestry of light. But what if in our mysterious galaxy, the interstellar medium itself is not diverse at all? What if its physical conditions are so unusually uniform and extreme that it behaves like one single, colossal entity? This idea transforms the galaxy from a collection of individual objects into a gigantic cosmic neon sign. Think about how a neon light works here on Earth. You take a sealed glass tube filled with a specific gas like neon or argon. Then you run a powerful electric current through it. This electrical energy violently excites the gas atoms, bumping their electrons into higher energy levels. When those electrons fall back down, they release that energy as light, but only at very specific, precise wavelengths determined by the unique atomic structure of that gas. Neon glows a characteristic orange-red, while argon produces a bluish hue. The color is pure and singular because the conditions inside the tube are engineered to be perfect for exciting only that one type of atom. Now scale this idea up to a galactic level. Imagine that the entire vast expanse of PGC 0451112 is permeated by an incredibly uniform and immense cloud of hydrogen gas. Then, some kind of pervasive energy field, whether from a hidden quasar, a population of hot stars, or even dark matter, washes through this entire cloud. If the density and temperature of this galactic hydrogen are just right throughout, the entire cloud could be triggered to fluoresce in unison. Instead of isolated nebulae glowing around individual stars, the whole galaxy lights up as one coherent unit. The intense, monochromatic red light we see would then be the signature of hydrogen atoms across 100,000 light years, all being excited in exactly the same way, emitting their characteristic hydrogen alpha photon in a synchronized cosmic display. The galaxy isn't just containing neon signs, it has become one. For this to happen, the physical state of the interstellar medium would have to be extraordinarily peculiar. Normally, the gas in a galaxy is a turbulent mess. Supernova explosions create gigantic hot bubbles, while gravity pulls matter into cold, dense filaments. This creates a wide range of densities and temperatures, which in turn produces a complex mix of light emissions. But in our galaxy, the evidence suggests an eerie uniformity. The sheer purity of the hydrogen alpha emission line, its narrowness and strength, hints that the glowing gas is all at a very similar temperature and density. There's no sign of the broad emission lines that would come from gas being violently churned and accelerated, as you would find near a black hole or in a starburst region. This points to a calm, stable, and widespread environment, a placid ocean of gas being steadily illuminated by a diffuse energy source. The question then becomes, what could create and maintain such a bizarrely uniform interstellar medium? One possibility is that this galaxy is incredibly anemic, having lost or never possessed the ingredients for a normal stellar life cycle. Without stars, there are no supernova to stir the gas, no stellar winds to carve out bubbles, no planetary systems forming to lock away dust. The interstellar medium could have settled into a state of profound equilibrium, a vast, quiet reservoir of pristine hydrogen. Any energy introduced into this system would propagate smoothly, causing the entire cloud to glow with a single, pure color, much like a perfectly tuned laser. This explanation paints a picture of a galaxy in a state of suspended animation, a ghostly beacon whose light is a direct consequence of its own profound simplicity and stillness. Peering into the heart of this monochromatic mystery is a monumental technical challenge in itself. While its unusual light signature first alerted us to its existence, truly understanding PGC 04511112 requires us to move beyond a simple fingerprint and dissect the galaxy with the precision of a cosmic surgeon. The primary obstacle is its staggering distance and inherent faintness. From 750 million light-years away, it appears as little more than a faint, unresolved smudge of red in most telescopes. This presents a fundamental problem. We need to know how the galaxy's light is distributed across its structure. Is the red glow concentrated in a brilliant, compact core, suggesting a central power source like a hidden quasar? Or is it spread evenly throughout the entire galactic disk, pointing toward a galaxy-wide phenomenon like a unique stellar population or dark matter glow? With standard imaging, we simply cannot tell. We are like an art historian trying to determine the brushstrokes of a masterpiece by looking at a thumbnail-sized photograph from across a dimly lit room. The critical spatial information is lost, blurring all the clues into a single, enigmatic data point. To overcome this, astronomers turn to one of the most advanced techniques in modern astronomy, integral field spectroscopy. Think of a regular telescope as a camera that takes a color picture. An integral field spectrograph, however, is like a camera that takes a picture where every single pixel is its own miniature rainbow. This powerful instrument effectively places a tiny prism over each point of light in the image, allowing scientists to capture a full spectrum from dozens or even hundreds of distinct locations across the face of the galaxy simultaneously. It transforms that faint red smudge into a rich, three-dimensional data cube, 2 dimensions of space and 1 dimension of wavelength. With this tool, astronomers can create maps. They can generate a map showing where the hydrogen alpha emission is strongest, a map of the gas's velocity, showing if it's rotating or flowing inward, and even maps searching for the faint traces of other elements that might be hiding in the glare. This technique is essential for distinguishing between our competing hypotheses. If the red light is emanating from a single, pinpoint location, it strongly supports the hidden quasar model. If it's coming from several star-forming knots, it might point to a starburst. And if the glow is smooth and uniform across the entire galaxy, it would be powerful evidence for the more exotic explanations involving a pristine chemical makeup or dark matter. Even with this sophisticated technology, the observations push our instruments to their absolute limits. The light signal is so weak that it requires incredibly long exposure times, keeping the telescope locked on the galaxy for many hours, sometimes over multiple nights, to collect enough photons for a clear analysis. Every second of observation is precious and fiercely competed for on the world's largest telescopes. Furthermore, Earth's own atmosphere acts as a constant adversary. The turbulence that makes stars twinkle also blurs the fine details of distant galaxies, smearing out the very structures astronomers are desperate to resolve. To combat this, many of these studies rely on adaptive optics systems, which use a powerful laser to create an artificial guide star in the upper atmosphere. Sensors then measure the atmospheric distortion in real time, and a computer-controlled flexible mirror deforms its surface hundreds of times per second to cancel out the blurring effect. It's a breathtaking feat of engineering, a high-speed dance of light and mechanics, all to bring a tiny, red speck at the edge of the observable universe into sharper focus. The interpretation of this hard-won data is another minefield of challenges. The velocity of the gas, for instance, is measured by the Doppler shift, the slight reddening or bluing of the hydrogen alpha line as the gas moves away from or toward us. But untangling this signal is complex. Is the smooth rotation curve of a serene, stable galaxy, or is it the chaotic churning of gas being violently stirred by an outburst from a central black hole? The answers are not always clear-cut, and a single observation can often support more than one theory, requiring ever more precise follow-up studies. Each new piece of data is like finding a single piece of a jigsaw puzzle without knowing what the final picture is supposed to be. The work on PGC 0451112 represents astronomy at its most challenging and collaborative, a global effort that combines cutting-edge technology, painstaking data analysis, and theoretical ingenuity just to ask the next right question about this most peculiar of cosmic wonders. To fully appreciate the profound strangeness of PGC 0451112, it helps to survey the cosmic zoo of other galactic oddities. Our universe is teeming with peculiar galaxies, each a unique experiment in stellar and gravitational physics. But even among these outliers, our monochromatic enigma stands apart in a class of its own. Consider, for instance, the green pea galaxies, discovered by citizen scientists in the data of the Sloan Digital Sky Survey. These are small, compact galaxies that glow with an intense emerald green light. This green hue comes not from a single wavelength, but from a powerful combination of emission lines, primarily from highly ionized oxygen. Green peas are stellar firestorms, undergoing such ferocious bursts of star formation that their entire structure is lit up by the energetic radiation from countless newborn stars. They are bizarre, but their weirdness is easily explained by a known, if extreme, astrophysical process. They are a shout, while PGC 0451112 is a solitary, unwavering note. Then there are the ultra-compact dwarf galaxies, or UCDS. These are enigmatic objects that pack hundreds of millions of stars into a region only about 200 light-years across, so dense that 1 million stars could fit within the space between our Sun and its nearest stellar neighbor. For a long time, astronomers debated whether they were the remnant cores of larger galaxies that had been stripped bare by tidal forces, or simply extremely massive globular clusters. Their peculiarity lies in their structure and density, a mystery of galactic architecture. Yet, when you analyze their light, a typical UCD presents a familiar spectrum, a mix of colors reflecting an old, red stellar population. Their strangeness is in their form, not the fundamental nature of their light. Our one-color galaxy, by contrast, has a normalist shape but an utterly abnormal spectral signature, a core anomaly that strikes at the heart of what we think powers a galaxy. This comparative approach is more than just cataloging curiosities. It is a fundamental method for defining the boundaries of galactic evolution. Every peculiar galaxy is like a word in a cosmic language, telling us about the physical processes that can shape matter. Tidal dwarf galaxies, formed from the debris of galactic collisions, teach us about the resilience of gas under extreme violence. Lenticular galaxies, which possess a disk like a spiral but lack its arms, represent a transitional, quiescent state between vibrant spiral and dead elliptical. Each one fits somewhere on a spectrum of understood, if rare, phenomena. PGC 0451112, however, refuses to fit on any existing spectrum. Its sheer spectral purity, the dominance of one emission line to the exclusion of all others, is what makes it such a stark outlier. It is not merely an extreme example of a known category, it appears to be a category of one. This uniqueness is precisely what makes it so scientifically valuable. In biology, the discovery of a platypus, a mammal that lays eggs, forced a re-evaluation of what it means to be a mammal. In astronomy, this galaxy is our cosmic platypus. Its existence challenges the very definition of a galaxy. Must a galaxy always be a diverse collection of stars? Can a vast cloud of uniformly glowing gas, powered by a single, unknown mechanism, truly be considered a galaxy in the same way as the Milky Way? By standing so far outside the norm, it forces us to question the rules we thought were universal. It pushes the envelope of galactic diversity, suggesting that the universe's recipe book for building islands of stars and gas might have a page we have never seen before, one that produces a result of breathtaking and puzzling simplicity. To understand when this strange transformation occurred, we need to look at a fundamental feature of its light, one that serves as a cosmic clock measuring its journey through an expanding universe, its redshift. The light from PGC 0451112 is not just red because of its hydrogen glow. Its very fabric has been stretched, shifting all its light toward the red end of the spectrum. This phenomenon, known as cosmological redshift, is caused by the expansion of the universe itself. As the galaxy's light travels across the vast emptiness of space for hundreds of millions of years, the space through which it moves is steadily stretching. This stretching elongates the light waves, much like drawing on a rubber band lengthens a line drawn on it. The amount of this stretch tells us precisely how long the light has been traveling, giving us a direct measurement of the galaxy's distance and, by extension, its place in cosmic history. The redshift measurement for this galaxy places it at a distance of approximately 750 million light-years away. This means the light we are seeing today left the galaxy when dinosaurs still roamed the Earth, a time that is, cosmically speaking, relatively recent. The universe is nearly 14 billion years old, so this galaxy is not a relic from the extreme infancy of the cosmos. It is not one of the very first galaxies that formed. It is a contemporary, more or less, of our own Milky Way. This timing is critically important as it immediately rules out some of the more exotic early universe explanations. We are not looking at a pristine population, three-star galaxy from the dawn of time. The universe had already been busily forging heavier elements for over 12 billion years by the time the light we see began its journey. Stars had been born, lived, and died, seeding the cosmos with the materials for planets and life. This galaxy, therefore, did not form in a primordial, empty universe. It grew up in a mature, chemically enriched cosmic environment. This fact makes its existence even more puzzling. If this galaxy is a product of the modern universe, why does it appear so primitive? Its apparent lack of heavy elements and its bizarrely simple light suggest a system that has somehow avoided the standard cycle of galactic evolution that has shaped every other galaxy we see. It's as if we found a bustling, modern city where, in one district, everyone still lives in simple wooden huts and uses stone tools, completely isolated from the technological advances surrounding them. The conditions that allowed for such an anomaly to persist until 750 million years ago must be incredibly rare and specific. It suggests this galaxy has lived an unusually sheltered life, perhaps in a cosmic backwater, a vast void in the large-scale structure of the universe where it has had very few interactions with other galaxies. Isolated from the mergers and gas accretion that typically trigger star formation and chemical enrichment, it could have remained in a state of arrested development, a quiet pocket of simplicity in an otherwise complex and evolving cosmos. Alternatively, the redshift tells us that we might be witnessing not a preserved relic, but a very late blooming event. Perhaps this galaxy spent most of its life as a normal but quiescent collection of gas and dark matter. Then, relatively recently in cosmic terms, something happened. A close encounter with another galaxy, the slow accumulation of gas from intergalactic space, or the ignition of its central black hole could have triggered a delayed but intense period of activity. This event would then be lighting up the galaxy in this unique way. The fact that we see it now shining with such a pure light could mean we have caught it at a very special and fleeting moment in its long life. We might be seeing a short-lived phase that most galaxies pass through quickly, but which this one is experiencing for the first time or in an unusually prolonged manner. The redshift, therefore, doesn't just give us a date, it frames the mystery, forcing us to ask not just what this galaxy is, but why it became this way at this particular chapter in the story of the universe. Faced with a real-world observation that defies easy explanation, astrophysicists turn to their most powerful tool for testing ideas, the supercomputer. These machines allow them to build entire universes from the ground up, governed by the laws of physics as we understand them, to see if they can spontaneously produce something that looks like our mysterious red galaxy. This process is less about creating a perfect digital replica and more about a rigorous form of scientific experimentation. The goal is to take each of our proposed explanations, the quasar filter, the pristine stellar population, the dark matter glow, and push them to their logical extremes within a simulated environment. Can the known laws of physics, under a very specific and rare set of starting conditions, give birth to such a spectral purist? The first challenge in this digital detective work is establishing the initial conditions for the simulation. For the primordial galaxy hypothesis, scientists would start with a vast cloud of simulated gas containing only hydrogen and helium, perfectly pristine as it would have been just after the Big Bang. They would place this cloud in a region of simulated space that is remarkably isolated, a cosmic desert where it would be shielded from the pollution of supernova from neighboring galaxies for billions of years. Then they would let gravity take over. The critical question becomes, does this pristine gas collapse to form a population of stars that is monochromatic in its effect? The simulations often show that without heavier elements to aid cooling, the first stars to form are indeed monstrously large and hot, bathing their surroundings in intense ultraviolet light that would produce a strong hydrogen alpha glow. However, a major hurdle emerges almost immediately. These massive stars are incredibly unstable. They live for only a few million years before exploding as supernova, and these explosions do two things that break the model. First, they violently churn and disrupt the interstellar gas, creating a complex and turbulent environment rather than a uniform glow. Second, and more importantly, they seed the galaxy with the first heavy elements, ensuring that the next generation of stars will be different, ultimately leading to the diverse stellar population we see in normal galaxies. For a galaxy to remain monochromatic for hundreds of millions of years, the simulation must find a way to suppress this natural progression, a stability that has so far proven incredibly difficult to achieve. When testing the obscured quasar idea, the simulations become even more intricate. Astrophysicists model a supermassive black hole at the center of a galaxy, feeding it a steady stream of gas to create a brilliant accretion disk. Then they encase this central engine in a thick, dusty torus. The simulation must then track not just the gravity and hydrodynamics of the gas, but also the intricate journey of light particles or photons as they travel through this complex system. The key is to see if a viewing angle exists a specific orientation relative to the torus where the direct light from the quasar is completely blocked, but its energy still manages to leak out and excite a large surrounding reservoir of hydrogen gas. Some simulations have shown that this is theoretically possible, creating a galaxy whose observed light is dominated by extended emission lines. However, reproducing the stunning purity of PGC 04511112 spectrum is another matter. The violent environment around a quasar typically heats gas to a wide range of temperatures and accelerates it to high velocities, which should produce broadened emission lines from many different elements. Getting the simulation to produce a spectrum that is almost exclusively a narrow hydrogen line requires fine-tuning the system to an almost unimaginable degree, suggesting that if this is the answer, we are witnessing a cosmic configuration of exquisite rarity. The most speculative and fascinating simulations involve dark matter. Here, physicists input the proposed properties of a theoretical dark matter particle, its mass, and its likelihood to annihilate or decay into photons. They then create a simulated galaxy with an unusually high concentration of this dark matter in its halo. The simulation calculates the rate at which these particles would interact and how the resulting energy would be deposited into the ordinary hydrogen gas within the galaxy. The success of these models depends entirely on the specific properties chosen for the dark matter. If the particle is too light or interacts too weakly, the resulting glow would be far too faint to explain the intense red light we see. If it is too heavy or interacts too strongly, it would have been detected by other experiments by now. The simulation that perfectly matches the observation would therefore be a monumental breakthrough, as it would not only explain the strange galaxy, but also reveal the fundamental identity of dark matter itself. The failure of these models is equally informative. If no reasonable dark matter parameters can produce the monochromatic glow, it tells us that we may need to look for explanations within the realm of ordinary matter after all. The true power of these simulations lies not just in their successes, but in their revealing failures. When a model consistently fails to produce the desired outcome, it forces scientists to re-examine their underlying assumptions. Perhaps our understanding of star formation in metal-poor environments is incomplete. Maybe the behavior of gas around a feeding black hole is more complex than our current equations can capture. Each dead end in the simulation narrows the possibilities, guiding observers toward what to look for next with their telescopes. The dialogue between the digital universe and the real one is a continuous cycle of prediction and observation. A simulation might suggest that if the quasar theory is correct, we should detect a specific, faint signature in the X-ray spectrum. Observers then point the Chandra X-ray Observatory at the galaxy to check. If the signature is found, the theory gains credibility. If it is absent, the model must be revised or abandoned. This iterative process, though slow and painstaking, is how a cosmic anomaly gradually transforms from an inexplicable outlier into an understood, if exceptional, phenomenon. The mystery of the single-color galaxy is currently putting our best models to the test, and the fact that they are struggling to explain it is a thrilling indication that we are on the verge of learning something fundamentally new about the cosmos. So the hunt is on. With one confirmed oddity like PGC 04511112, the immediate and crucial question for astronomers is a simple one: is it alone? Is this galaxy a true cosmic unicorn, a singular fluke of nature that, through a bizarrely specific chain of events, ended up in a state unlike anything else? Or have we simply been missing an entire family of similar objects because we weren't looking for them in the right way? Finding the answer to this question is perhaps the single most important next step in solving this mystery, because the difference between a category of one and a new class of objects completely changes its scientific significance. A solitary freak can be explained away as a statistical anomaly, a 1 in a trillion chance, but a class of objects implies that there is a valid, repeatable pathway in the universe's recipe book for creating such spectral purists, a pathway we need to understand. This search is not as straightforward as simply pointing a telescope at the sky and looking for other red smudges. The initial discovery was a happy accident, a needle found in a haystack of millions of galactic spectra from the Sloan Digital Sky Survey. To find more needles, astronomers have had to build a better magnet. They are now designing sophisticated computer algorithms to automatically sift through the massive archives of spectral data from current and past surveys. But this time, they are programming them to search for one specific, bizarre signature, a spectrum that is dominated by a single, strong emission line with an otherwise eerily flat continuum. The challenge is immense, as there are many things in space that can mimic this signal. For instance, a distant quasar whose light has been heavily reddened by dust might appear to have a strong line, or an emission line star within our own galaxy could be misclassified. Each candidate requires meticulous follow-up observation to confirm its distance and rule out these false positives. It is a painstaking process of elimination, separating the true cosmic anomalies from the mundane imposters. The potential implications of this search are staggering. If we were to find even a handful of other galaxies with this same starkly monochromatic light, it would instantly transform PGC 04511112 from an inexplicable outlier into a valuable representative of a new galactic species. This would be a monumental shift. Suddenly, every theory proposed to explain it would be tested not against a single data point, but against a small population. We could begin to look for patterns. Do all these galaxies exist in cosmic voids, supporting the idea of isolated, primitive environments? Are they all found near massive galaxy clusters, lending credence to the gravitational lensing mirage theory? Perhaps they all show subtle signs of central activity in X-rays, pointing toward the hidden quasar model. A class of objects provides statistical power, allowing scientists to identify common traits and rule out explanations that only work for one specific case. Furthermore, discovering more of these galaxies would allow us to study how they might change over time. By finding them at different distances and therefore different ages in the universe, we could potentially see this monochromatic phase as a stage in a galactic life cycle. Maybe it is a fleeting state that many galaxies pass through after a major merger, a brief period of intense, focused emission before settling down into a more normal existence. If we can find examples at various points along this timeline, we could piece together the entire story, watching a galaxy evolve into and then out of this strange condition. This would turn them from static puzzles into dynamic characters in the narrative of cosmic evolution. The search itself is also pushing the capabilities of our newest and most powerful observatories. The James Webb Space Telescope, with its unparalleled sensitivity in the infrared, is a game changer for this hunt. It can peer deeper into the universe than ever before, looking for faint, distant examples of these objects that would be invisible to other telescopes. Its sophisticated instruments can also take incredibly detailed spectra of candidate galaxies, allowing us to analyze their chemical composition with a precision that was previously impossible. We could definitively confirm or rule out the primordial galaxy hypothesis by measuring their metallicity with unprecedented accuracy. Each new tool we build expands the search, increasing the chances that we will find others and finally understand the true nature of the galaxy that for now shines in a color all its own. The quest to find its kin is more than a census. It is a direct investigation into the diversity of physical laws and the hidden pathways of galactic life. The existence of a galaxy like PGC 04511112 sends ripples through the entire field of galactic astronomy. forcing a re-examination of the standard story we tell about how galaxies are born, live, and die. For decades, our models have been built upon observations of thousands of galaxies, painting a picture of a coherent, if complex, life cycle. We thought we had a good grasp on the major chapters. But this monochromatic anomaly is like finding a page in the cosmic history book written in a language we don't understand, suggesting there are entire paragraphs of the story we've missed. The central question it raises is profound. Is this galaxy a brief, universal phase that has simply been too fleeting to catch, or is it a strange evolutionary dead end, a path so rare that most galaxies never take it? If this single color state is a short-lived phase, then our models aren't wrong, they are just incomplete. Imagine a caterpillar's transformation into a butterfly. The process is well understood, but if you only ever looked at caterpillars and butterflies, you would have no knowledge of the chrysalis, the quiet, transformative stage in between. PGC 0451112 could be our first glimpse of a galactic chrysalis. Perhaps every galaxy, after a major event like a collision or a sudden infusion of cold gas, goes through a period where its light is dominated by a single, intense process. For a normal galaxy, this phase might last only a few tens of millions of years, a mere blink of an eye on cosmic timescales. In the grand sweep of a galaxy's 10 billion-year life, catching it in this specific moment would be incredibly rare. Our standard telescopes, which snap a single picture in time, would almost always see galaxies either before or after this brief outburst, explaining why it has remained so elusive. This interpretation is comforting. It suggests the galaxy is not an exception to the rules, but a key to understanding a subtle yet critical stage in the rulebook itself. On the other hand, if this galaxy represents a dead-end path, its implications are far more disruptive. This would mean that the universe allows for galactic outcomes that lie completely outside our current evolutionary trees. Think of the diversity of life on Earth. While most species follow predictable evolutionary paths, some branch off into highly specialized niches that lead nowhere else. The koala, for instance, evolved to eat only eucalyptus leaves, a successful strategy in its specific environment, but one that limits its future possibilities. Similarly, PGC 0451112 might be a cosmic koala. It may have formed under such peculiar initial conditions, perhaps in an extreme void with a very specific mix of dark matter and pristine gas, that it embarked on an evolutionary trajectory that most galaxies avoid. It became specialized, emitting its pure red light, but in doing so, it may have locked itself into a state from which it cannot easily evolve into a more complex system rich with stars and planets. It is a viable, stable outcome, but one that represents a terminus, not a transition. This challenge to textbook narratives is particularly sharp when we consider the concept of metallicity, the abundance of heavy elements, as the engine of galactic growth. The standard story is one of steady enrichment. A galaxy starts with pristine gas, forms its first massive stars, which then explode and seed the environment with metals. These metals allow the next generation of stars to form more efficiently, leading to greater diversity, planetary systems, and ultimately, the potential for chemistry that could support life. It's a story of increasing complexity. PGC 0451112 stands in stark opposition to this narrative. Its apparent lack of heavy elements suggests it has somehow broken this cycle. It has either failed to produce multiple generations of stars or has managed to expel the enriched material, remaining in a state of perpetual simplicity. This forces astronomers to ask what physical processes could halt enrichment. Are there galactic feedback mechanisms we haven't accounted for, perhaps driven by dark matter or magnetic fields, that can purge a galaxy of its metals and reset it to a primitive state? The existence of this galaxy suggests that the journey from simplicity to complexity is not a one-way street. under the right conditions, a galaxy can seemingly remain forever young, or even revert to a more primitive form. Ultimately, the greatest implication might be a humbling one. Our models of galaxy evolution are based on a biased sample. We have built our understanding primarily by studying the galaxies that are brightest, closest, and easiest to see, the cosmic equivalents of streetlights in a vast, dark landscape. These tend to be the large, successful, and chemically rich galaxies. PGC 04511112 is a faint, subtle object that was only discovered by sifting through massive data sets. It raises the terrifyingly exciting possibility that we have been missing a significant population of faint, strange galaxies that don't play by the same rules. The cosmos might be filled with these quiet, peculiar objects, each following its own unique evolutionary path. If that is true, then our current textbooks don't just need a new chapter, they may need to be rewritten from the introduction, acknowledging that the universe has a far richer and more diverse imagination for creating galactic life than we ever dreamed. But to truly appreciate how a galaxy could become so focused, we need to consider the cosmic thermostat that governs all galactic ecosystems: feedback. In a normal galaxy, there's a delicate balance between the forces of creation and destruction. Stars are born from collapsing clouds of gas, but the most massive of these stars don't just sit idly by. They live fast and die young, exploding as supernova. These violent deaths blast tremendous energy back into the surrounding gas. This energy does two things. It can compress nearby gas clouds, triggering the birth of more stars, but it can also heat the gas to such extreme temperatures that it is blown away, preventing further star formation for millions of years. This self-regulating process, where stars themselves control the rate at which new stars are born, is a classic form of feedback. It's why galaxies don't convert all their gas into stars in one frantic burst, but instead form stars at a relatively steady pace over billions of years. Now imagine this process pushed to an absolute extreme. What if a feedback mechanism wasn't just a regulator, but a total dominator? This idea provides a powerful framework that could tie together several of our previous hypotheses. Picture a galaxy in its youth, bustling with a normal, diverse population of stars. Then, a cataclysmic event occurs, perhaps the ignition of its central supermassive black hole into a brilliant quasar, or an incredibly intense and concentrated starburst. The energy output from this event would be unimaginable, far surpassing the gentle feedback of ordinary supernova. This isn't a thermostat adjustment, it's a furnace door being flung open. A colossal wave of energy, in the form of radiation and powerful particle jets, sweeps through the galaxy like a cosmic hurricane. This is where the concept of extreme feedback offers a compelling explanation for our monochromatic mystery. This hurricane of energy would have a selective effect on the galaxy's gas. The cooler, denser clouds of gas that are the nurseries for sun-like stars would be utterly devastated. They would be heated, dispersed, and effectively sterilized, shutting down the formation of any future low-mass stars permanently. However, the feedback might not be equally destructive to all star formation. If the conditions were just right, this immense energy blast could trigger a very specific and unusual outcome. It could compress the remaining, more diffuse hydrogen gas into a vast, hot, and uniformly distributed cloud. Within this heated environment, only the formation of extremely massive, hot stars might be possible. These stars would be few in number but incredibly powerful, and their intense ultraviolet light would be perfect for exciting the surrounding hydrogen gas into that brilliant, uniform red glow. In this scenario, feedback hasn't just suppressed star formation. It has engineered the galactic environment to produce only one type of stellar actor, which in turn produces only one color of light. This extreme feedback model elegantly connects the quasar and starburst ideas. A ferocious burst of star formation could provide the initial energy blowout, or a quasar's awakening could be the primary engine of destruction. In either case, the result is a galaxy whose evolutionary path has been violently narrowed. The feedback loop becomes a one-way street. The event shuts down normal, diverse star formation, leaving behind a system where the only ongoing activity is the emission of light from the excited hydrogen gas, fueled by the last generation of stars that the feedback conditions themselves allowed to form. It transforms the galaxy into a specialized entity, its complexity stripped away by its own most powerful internal forces, leaving behind a singular, brilliant signature of a profound and transformative event in its deep past. Whenever we are confronted with a phenomenon that defies our current understanding, it is almost a natural human impulse to ask one of the most profound questions of all: could this be a sign of intelligence? Could the singular, monochromatic light of PGC 0451112 be not a natural wonder, but a cosmic engineering project on an unimaginable scale? This idea, known as the search for technosignatures, ventures into the realm of what is often called the zoo hypothesis, or more specifically, a Type 3 civilization on the Kardashev scale, a civilization capable of harnessing the entire energy output of its host galaxy. While scientists must approach this possibility with extreme caution, it is a speculative angle that captures the imagination and deserves to be explored, if only to understand why the natural explanations remain so much more compelling. Imagine a civilization so advanced that its energy needs have grown beyond planetary or stellar systems. To power its endeavors, such a culture might seek to enclose its entire galaxy, or at least a significant portion of it, within a vast structure, a concept reminiscent of a Dyson sphere but scaled up to a galactic level. This hypothetical megastructure, sometimes called a galactic engine or a Sijkadov thruster, would be designed to capture and utilize the light from every star. In the process of constructing such an artifact, the civilization might need to filter or process the galaxy's light in very specific ways, perhaps to direct energy or to create a stable environment. Could the pure red hydrogen alpha glow we see be the unintended byproduct or even an intentional signal of such a project? It's a staggering thought that we might be looking not at a galaxy, but at the greatest public works project in the history of the universe. Another fascinating, though equally speculative, idea is that the light itself is a message, a beacon. If you wanted to announce your existence across the vast gulfs of interstellar space, how would you do it? A radio signal is one possibility, but it is narrow and directed. A beacon visible across millions of light years, however, would be a billboard on a cosmic highway. Engineering an entire galaxy to emit a single, unmistakable wavelength of light would be a way to say, "We are here," in a language that any developing civilization with a telescope could eventually understand. The purity of the signal is what would make it artificial. Nature, as we know it, is messy and complex. A single, unwavering color is the hallmark of a laser, not a star. In this scenario, the galaxy's light is not a natural phenomenon but a deliberate technological creation, a calling card left for the universe to find. Despite the captivating nature of these ideas, the scientific community places them at the very bottom of the list of likely explanations, and for several very good reasons. The first and most important is the principle of Occam's razor. When faced with a mystery, the explanation that requires the fewest new assumptions is usually the correct one. Invoking a hyper-advanced alien civilization requires us to assume not only that such beings exist, which is statistically plausible, but that they have capabilities far beyond our understanding of physics, that they would choose to express those capabilities in this specific, energy-intensive way, and that we happen to be observing it at this precise moment in cosmic history. A natural explanation, no matter how exotic, only requires that we have an incomplete understanding of astrophysics, which we know for a fact to be true. The history of science is littered with mysteries initially attributed to the gods or other intelligent agents, from lightning to the movement of planets that were later explained by natural laws. The prudent approach is always to exhaust every possible natural cause before leaping to a supernatural, or in this case, extraterrestrial one. Furthermore, a technosignature hypothesis must be falsifiable to be scientifically useful. That is, there must be a way to test it and potentially prove it wrong. Currently, the alien megastructure idea is more of a thought experiment than a testable theory. What specific, observable prediction does it make that distinguishes it from, say, the obscured quasar or the primordial galaxy hypothesis? If we were to discover that the light varies in a complex coded pattern, that would be compelling evidence. If we found that the galaxy's shape was geometrically perfect, that would be a strong indicator. But so far, the data we have for PGC 04511112, while strange, fits comfortably within the realm of known physical phenomena, even if we haven't pinpointed the exact one yet. Its light is steady, its shape is irregular and natural looking. There is no obvious signature of design or encoded information. Until such a signature is found, the idea remains in the domain of exciting speculation rather than serious scientific inquiry. This responsible skepticism, however, does not diminish the value of asking the question. The very act of considering a technosignature forces us to think critically about what we mean by natural. It pushes us to define the boundary between the possible and the impossible within the laws of physics. It also highlights the profound importance of continued observation. The same telescopes and techniques being used to test the natural hypotheses, searching for hidden X-ray sources, mapping the gas velocities, measuring the chemical composition, are also the very tools that could one day uncover a truly inexplicable pattern that points toward intelligence. The search for extraterrestrial intelligence is not separate from mainstream astronomy. It is a part of it, a subtle undercurrent in the analysis of every anomalous signal. So, while the leading explanations for our red galaxy involve quasars, primordial stars, or dark matter, the remote possibility that we are witnessing something even more extraordinary serves as a powerful reminder of why we look up at the stars in the first place, not just to understand the universe, but to see if anyone else is out there understanding it with us. The key to unlocking this cosmic riddle may now be in the hands of our most powerful eye on the sky, the James Webb Space Telescope. While previous observatories have given us the mystery, Webb is uniquely equipped to deliver the solution. Its revolutionary design centers on an unparalleled sensitivity to infrared light, which is not just an upgrade but a fundamental shift in our ability to probe the hidden details of objects like PGC 04511112. Think of infrared light as a universal skeleton key for astronomy. It slips past cosmic dust that blocks visible light. It reveals the heat signatures of cool objects, and because of the expansion of the universe, the light from the most distant objects is stretched into the infrared part of the spectrum by the time it reaches us. For a galaxy that is both distant and potentially shrouded in mystery, Webb is the perfect detective. Its first major task will be to conduct a deep and precise chemical analysis. Webb's spectrographs can take the faint light from this galaxy and break it down into an exquisitely detailed rainbow, searching for the faintest traces of elements that have so far remained invisible. Can it detect even a whisper of oxygen or nitrogen? If the spectrum remains starkly pure, with no heavy element lines, the case for a primordial or incredibly metal-poor galaxy becomes incredibly strong. Conversely, if Webb uncovers a hidden complex chemistry, it would immediately rule out the relic star hypothesis and point toward a more contemporary, if bizarre, phenomenon. This isn't just about confirming what's there, it's about definitively ruling out what isn't, a critical step in narrowing the field of competing theories. Perhaps even more exciting is Webb's ability to resolve the galaxy's structure. Until now, it has been a single, unresolved smudge of red. But Webb's massive mirror and location in the stable environment of space allow it to see with stunning clarity. It will attempt to pierce the haze and create a detailed image, mapping where the light is actually coming from. Is the intense red glow concentrated in a brilliant, pinpoint nucleus, screaming the presence of a hidden quasar? Or is it smoothly distributed across a vast, faint disk, which would be a hallmark of a galaxy-wide process like a unique stellar population or even dark matter interaction? This single image could instantly validate one major hypothesis and discard several others, providing a spatial context that has been completely missing from the investigation. The telescope might even be powerful enough to do the seemingly impossible, detect individual stars within this distant galaxy. If the galaxy is indeed powered by a population of massive hot stars, Webb's infrared vision could potentially pick out the brightest of these giants. Studying the light from these individual points would be like conducting a census of the galaxy's population, telling us their temperatures, masses, and ages directly. This would move us from inference to direct observation, transforming the mystery from a puzzle about a blurred whole into a solvable question about its constituent parts. The data returned will be so rich that it will keep astronomers busy for years, not just for this one galaxy, but as a template for understanding any others like it that we might find. We are standing on the precipice of a potential revolution in our understanding. The James Webb Space Telescope represents our best chance to move from speculation to certainty, to replace a list of fascinating possibilities with a single, coherent story. Every hour of observation time on Webb is fiercely competed for by scientists around the world, and you can be sure that pointing its golden eye toward this enigmatic red smudge is a top priority. The answers it finds will not only solve the mystery of PGC 04511112, but will also refine our models of galaxy evolution for every galaxy we see. We are about to learn whether we've discovered a cosmic missing link, a galactic ghost, or something entirely new that will force us to write a new chapter in the book of astronomy. Beyond the technical details and competing theories, the existence of this galaxy forces us to confront a much deeper, almost philosophical question about the nature of the universe itself. For centuries, our scientific journey has been guided by a belief in an underlying order, a set of elegant mathematical rules that govern everything from the fall of an apple to the spin of a galaxy. We've embraced complexity because we believe it emerges from simplicity. We look at the intricate whirl of a nebula or the baffling diversity of life and assume that beneath it all, there must be a beautiful, fundamental law. But what if we have it backwards? What if the universe's default state is not complexity, but an profound, even monotonous simplicity? The single-color galaxy presents us with a cosmic paradox, an object of breathtaking simplicity that, by its very existence, complicates our understanding. This idea resonates powerfully with a principle that has guided scientific inquiry for hundreds of years, Occam's razor. In its simplest form, it suggests that when you have multiple explanations for a phenomenon, the one that makes the fewest assumptions is usually correct. We naturally favor the straightforward story over the convoluted one. Our investigation into this galaxy has been a perfect exercise in applying Occam's razor. We started with the simplest explanation, a dusty galaxy, and when that was ruled out, we moved to more complex ideas like starbursts and hidden quasars. With each step, the explanations have had to become more elaborate, more exotic, but the galaxy itself has remained stubbornly, beautifully simple. Its light is a pure tone in a cosmos we expect to be a symphony. This forces us to ask, is our relentless drive to find complex mechanisms actually leading us astray? Could the simplest explanation of all be that the universe is simply capable of creating such pure, unadorned objects without the need for a fantastical sequence of events? Perhaps our struggle to explain PGC 04511112 reveals less about the galaxy and more about our own cognitive biases. As a species that evolved in an environment of immense complexity and diversity, we are pattern-seeking engines. We are trained to see the intricate connections in a forest ecosystem, the subtle social cues in a human face, the layered history in a piece of rock. We carry this expectation of richness into our study of the cosmos. When we look at a galaxy, we anticipate a messy, vibrant, and evolving system because that is what our experience on Earth has taught us to value. A galaxy that emits one color feels unnatural to us not because it violates a law of physics, but because it violates our deep-seated aesthetic and intellectual expectation of what a galaxy should be. It is a cosmic minimalist in a universe we have always interpreted as a Baroque masterpiece. This challenge extends to our very quest for a theory of everything, a single set of equations that can describe all forces and particles. That quest is the ultimate expression of our belief in underlying simplicity. We are trying to reduce the universe's magnificent complexity to a few lines of elegant mathematics. Yet here is a galaxy that appears to have already achieved a kind of physical simplicity, and we find it baffling. The irony is palpable. We are searching for simple laws to explain a complex cosmos, and when we stumble upon an object that seems to embody a radical simplicity, we are forced to invent increasingly complex models to understand it. It's as if the universe is gently mocking our efforts, presenting us with a riddle that suggests simplicity might not be a foundational law we discover, but a possible outcome that exists alongside complexity, one we are just beginning to recognize. Ultimately, the monochromatic galaxy is more than a scientific puzzle. It is a cosmic Rorschach test. What we see in its singular red glow reflects our own assumptions about order, chaos, and the nature of reality. For some, it is a testament to the universe's boundless creativity, its ability to produce outliers that defy categorization. For others, it is a humbling reminder of the limits of our knowledge, a sign that our current textbooks are merely rough drafts in a story that is far grander and stranger than we imagined. It teaches us that the universe is under no obligation to conform to our definitions of beauty, complexity, or even normalcy. Its greatest lesson may be to cultivate a willingness to be surprised, to embrace the anomaly not as a problem to be solved, but as a clue pointing toward a wider, wilder, and more wonderfully diverse cosmos than we ever thought possible. What makes a mystery like this so captivating is that it belongs to everyone. You don't need a PhD in astrophysics to look up at the night sky and feel a sense of wonder, or to be intrigued by the idea of a galaxy that glows with a single, strange color. This inherent curiosity is the engine of modern astronomy, and it's increasingly being harnessed through the power of citizen science. Across the globe, thousands of volunteers, teachers, artists, engineers, and students are logging onto their home computers and becoming active participants in the search for cosmic answers. These are not just passive observers, they are becoming an essential part of the research team, helping professional astronomers sift through the mountains of data that our digital telescopes now produce. The discovery of PGC 04511112 itself is a testament to this collaborative spirit. It was found within the colossal dataset of the Sloan Digital Sky Survey, a project that has mapped over a third of the sky. But with millions of galaxies catalogued, how do a handful of researchers possibly find the one in a million anomaly? The answer often lies in projects like Galaxy Zoo, one of the most successful citizen science initiatives ever created. On the Galaxy Zoo website, anyone can be presented with a real, often never before seen, image of a galaxy taken by a robotic telescope. The task is simple but profound. Just look at the galaxy and classify its shape. Is it a spiral, an elliptical, or does it look like something else? The human brain is exceptionally good at pattern recognition. often outperforming even the most sophisticated computer algorithms at spotting the weird, the unusual, and the beautiful messiness that signifies something new. It was through this very process that citizen scientists first identified the class of small, greenish galaxies nicknamed green peas, which we mentioned earlier. Nobody told them to look for green galaxies. They simply noticed oddities that didn't fit the standard categories and flagged them for further study. This is the beautiful chaos of crowdsourced discovery. A retiree in Florida, a high school student in Norway, or a night shift worker in Australia can, with a single click, bring a cosmic secret to light. The mystery of the single-color galaxy is now part of this same ecosystem. Astronomers can train new algorithms and create new citizen science projects specifically designed to search through spectral data, asking volunteers to look for the telltale signature of a spectrum dominated by one single towering emission line. Every pair of eyes that scans the data increases the chance that we will find another example, turning a solitary freak into a new class of object. This transforms science from a remote ivory tower endeavor into a genuinely human pursuit. It reinforces the idea that unraveling the universe's greatest mysteries is not a solitary task for a genius in a lab, but a collective, global effort. When a new peculiar galaxy is discovered with the help of citizen scientists, their names are often included in the resulting scientific papers. They become co-authors, their contribution permanently etched into the scientific record. This shared ownership of discovery builds a powerful bridge between the public and the scientific community, fostering a deeper appreciation for the painstaking and sometimes serendipitous nature of research. It's a reminder that every major breakthrough usually starts with someone simply noticing that something is different and having the curiosity to ask why. In the quest to understand the galaxy that emits only one color, the next crucial observation might not come from a billion-dollar telescope, but from the keen eye of an amateur astronomer gazing at the cosmos from their backyard, reminding us all that the universe is a story we are writing together. So we have journeyed through a landscape of cosmic possibilities, from cosmic dust to stellar firestorms, from hidden monsters to relics of creation, and even to the faint glow of dark matter itself. Each theory presents a compelling, self-contained narrative for why PGC 0451112 shines with such singular purpose. But standing here at the crossroads of these explanations, it's time to bring them all together and weigh the evidence. Think of it as assembling the pieces of a puzzle, examining each one to see which fits the picture best and which might be from a different box entirely. Let's start with the idea of a hidden starburst. The appeal here is its familiarity. We know starburst galaxies exist and they produce intense hydrogen alpha light. The evidence in its favor is the sheer power of the emission, which requires a tremendous energy source that massive young stars could provide. However, the case against it is strong. Where are the other emission lines from oxygen and nitrogen that always accompany such stellar frenzy? And critically, why is there no sign of the intense infrared glow that should come from dust warmed by all those newborn stars? The absence of these telltale signatures makes the starburst hypothesis a difficult one to sustain. Next, the obscured quasar theory. This one elegantly explains the energy problem. A supermassive black hole's accretion disk is one of the few things in the universe powerful enough to light up an entire galaxy. The evidence for it would be the discovery of high-energy X-rays or radio jets peeking through the obscuring material. The case against it, however, lies in the strange purity of the signal. A quasar's environment is chaotic, producing a broad spectrum of light and wide emission lines from many elements. To filter that down to a single, narrow hydrogen line requires a cosmic configuration of such precise fine-tuning that it seems almost too perfect to be true. Then we have the profound possibility of a primordial galaxy. This theory is a beautiful match for the galaxy's apparent lack of heavy elements and the sheer simplicity of its hydrogen-dominated spectrum. The evidence for it would be a definitive measurement showing an almost zero metallicity. The case against it is primarily one of timing. True population, 3 stars were thought to have died out billions of years ago. For a galaxy of them to exist just 750 million years ago, it would require it to have formed in a pocket of the universe that remained untouched for almost the entire history of the cosmos, a scenario that, while possible, is incredibly rare. We must also consider the gravitational lensing mirage. This is the ultimate "it's not you, it's me" explanation, suggesting the anomaly is a trick of perspective. The evidence for it would be finding a massive foreground galaxy cluster and observing a distorted, arc-like shape to the galaxy itself. The case against it is the galaxy's seemingly normal, undistorted appearance in initial images. For the lensing effect to work so perfectly as to filter out all light except one specific wavelength, the alignment would have to be astronomically precise. And finally, the most exotic contender, dark matter. This theory is thrilling because it connects a galactic mystery to the largest unsolved problem in physics. The evidence for it would be the correlation of the red glow with a region of exceptionally high dark matter density and the lack of any other viable power source. The case against it is that it remains entirely theoretical. We have no confirmed knowledge of a dark matter particle that could annihilate or decay in this way. It's a solution that first requires us to solve an even bigger mystery. To visualize this scientific showdown, imagine a table that lays out the competing ideas. In one column, the theory, starburst, obscured quasar, primordial galaxy, lensing, dark matter. In the next column, the key prediction, what we would expect to see if that theory is correct. For the starburst, its strong infrared emission and other elemental lines. For the quasar, its high-energy X-rays or radio jets. For the primordial galaxy, it's a spectrum with no heavy metals. For the lensing, it's a distorted shape and a foreground cluster. For dark matter, it's a glow that correlates perfectly with a dark matter halo and nothing else. And in a final column, the current status. For most, the evidence is inconclusive or missing, leaving the case wide open. This summary isn't a conclusion, but a roadmap for future discovery, highlighting the critical observations that will ultimately crack this cosmic case. The final verdict is still out, awaiting the next crucial piece of evidence from our telescopes. Despite the wealth of theories, the true nature of this galaxy remains one of astronomy's most compelling open cases. The investigation is far from over. In fact, the discovery has simply reframed the mystery, giving rise to a new set of precise, targeted questions that are now driving the research forward. The central, overarching question is no longer just what is it, but has become which single process can dominate a galaxy so completely. This shifts the focus from mere classification to understanding the fundamental physics of power and simplicity on a cosmic scale. Every piece of data we have is like a clue that points in multiple directions at once, and the scientific community is now engaged in a global effort to find the one piece of evidence that breaks the deadlock. The most immediate and urgent question concerns the galaxy's power source. We can measure the staggering intensity of the red hydrogen alpha light, which tells us the total amount of energy being pumped into the gas every second. The fundamental unknown is the engine generating that power. Is it a concentrated point source like a hidden quasar, or is it a diffuse, galaxy-wide phenomenon like a population of hot stars or dark matter decay? The next crucial observation, therefore, is a high-resolution map of the galaxy's structure. Astronomers are eagerly awaiting data from the James Webb Space Telescope that will finally answer this. If the light emanates from a brilliant, star-like point at the galaxy's core, the quasar hypothesis will surge to the forefront. If, however, the red glow is spread smoothly and evenly across the entire galactic disk, it would be powerful evidence for a more exotic explanation, forcing us to seriously consider the possibility of a truly unique stellar population or even a dark matter signature. A second major line of inquiry focuses on the galaxy's chemical composition. The startling purity of its light suggests an equally pure ingredient list, but is that truly the case? The current spectra hint at a severe lack of heavy elements, but the evidence is indirect. The next critical step is a deep, ultra-sensitive spectroscopic analysis to detect or definitively rule out the presence of other elements. Using Webb's incredible sensitivity, astronomers will search for the faintest whispers of oxygen or nitrogen emission lines that might be hiding in the glare of the hydrogen. Finding even a trace amount of these metals would immediately rule out the pristine population 3-star hypothesis and suggest a more contemporary, if bizarre, origin. Conversely, confirming a complete absence of heavy elements would be a monumental discovery, strongly supporting the idea of a cosmic relic and forcing a major revision of our models of how and when galaxies can form. Researchers are also intensely focused on the galaxy's environment. Is this object a solitary hermit, or does it have neighbors? The answer could hold the key to its history. A detailed survey of the surrounding cosmic volume is underway to map its local neighborhood. If the galaxy is found to be isolated in a vast, empty void, it would support theories that it has led a sheltered life, allowing it to avoid the mergers and interactions that typically trigger complex evolution. This isolation could explain how it retained its primitive state. On the other hand, if it is part of a group or cluster, it would suggest that its current state is the result of a recent dramatic event, like a galactic collision or a close encounter that stirred up its gas in a very specific way. Understanding its context is essential for determining whether its simplicity is a product of nurture or nature. The timeline of events is another major unknown. Are we witnessing a fleeting phase or a permanent state? The galaxy's redshift tells us when we are seeing it, but not for how long it has been this way or how long it will remain. The key to answering this is to find other, similar galaxies at different distances, and therefore different ages in the universe. A dedicated search is now on to find more monochromatic galaxies. If we can find a handful of them, and if they appear to be more common at certain cosmic epochs, it would indicate that this is a short-lived stage that many galaxies pass through. If, however, PGC 04511112 remains a solitary example, it suggests we are looking at an incredibly rare and stable endpoint, a cosmic dead end that represents a path less traveled in galactic evolution. Each new candidate discovered will provide another data point, helping to plot this strange phenomenon on the timeline of cosmic history. This active, multifaceted investigation is a perfect example of how modern science operates. It is not a solitary genius having a eureka, a moment, but a slow, collaborative, and global process of elimination. Astronomers from different institutions and countries are dividing the tasks, with some specializing in analyzing the Hubble data for structural clues, others preparing detailed observation proposals for the James Webb Space Telescope, and theoretical teams running ever more sophisticated computer simulations to test the limits of each hypothesis. Conferences feature dedicated sessions where researchers present their latest, often conflicting, interpretations of the same dataset. This healthy debate is the engine of progress, as each scientist points out the weaknesses in competing models and proposes new observations to test their own. The mystery of the single-color galaxy has become a fertile ground for scientific innovation, pushing the limits of our technology and our imagination, reminding us that the most exciting phrase in science is not eureka. But that's funny. And so our journey from a single, baffling day to point in a vast digital sky survey to the edge of our understanding of galactic life draws to a close. We have ventured through a labyrinth of possibilities, from cosmic dust and stellar firestorms to hidden black holes and the ghostly glow of dark matter itself. We've seen how a simple observation can unravel into a complex tapestry of questions, each more profound than the last. What began as a spectral anomaly has blossomed into a genuine cosmic puzzle, a challenge to the very definitions we use to categorize the universe. PGC 045112, a faint red smudge millions of light years away, stands as a powerful testament to a simple truth: we do not have all the answers. This is precisely what makes astronomy such a thrilling and living science. It is not a static collection of facts in a textbook, but a dynamic, ever-evolving conversation with the cosmos. Mysteries like this single-color galaxy are not roadblocks to progress. They are the very engine of discovery. They force us to question our assumptions, to refine our models, and to build ever better tools to peer into the darkness. Every anomaly, every outlier that refuses to fit neatly into our existing categories is a gift. It is the universe's way of tapping us on the shoulder and saying, "Look closer." There's more to the story than you thought. The greatest breakthroughs in human history have almost always sprung from a willingness to sit with the discomfort of not knowing and to pursue the strange, the unexpected, and the inexplicable with relentless curiosity. The allure of the cosmic unknown is what has drawn humanity to gaze at the stars for millennia. It is a fundamental part of our nature to seek understanding, to find patterns, and to tell stories about the world beyond our atmosphere. The mystery of this galaxy connects us directly to that ancient tradition of wonder. It reminds us that the universe is not obligated to conform to our expectations of beauty, complexity, or even logic. It is capable of creating things of breathtaking simplicity that, paradoxically, complicate our understanding in the most delightful ways. This peculiar object, shining its solitary red light across the vastness of space, is a beacon pointing toward the countless wonders that remain hidden, waiting for the right combination of technology, ingenuity, and curiosity to bring them into the light. So, as we await the next wave of observations from the James Webb Space Telescope and other instruments, the most important takeaway is not a definitive answer but an invitation. An invitation to embrace the questions themselves, to share in the collective excitement of not knowing. The story of this galaxy is still being written, and each one of us can be a part of it. By staying curious, by supporting scientific exploration, and by simply looking up at the night sky with a sense of wonder, we participate in the greatest detective story ever told. The next chapter in this cosmic mystery, and in countless others yet to be discovered, is just over the horizon. The universe has shown us one of its strangest cards. The game is far from over, and the revelations to come promise to be more astonishing than we can possibly imagine.